Welcome to the presentation of my thesis topic, that is OpenNARS for Applications Reasoner, Architecture and Application. This reasoner was also built to answer the research question whether and how a NARS implementation is able to enhance the autonomy of intelligent agents beyond the state of the art. The objectives here are to create a NARS implementation design which is suitable for autonomous agent, and to implement it in a portable and high performance manner. Then to evaluate it, to compare it with other techniques in experiments where adaptation at runtime is crucial. This system is a non-axiomatic reasoning system design, and the non-axiomatic reasoning system is a general-purpose reasoning system proposed by Dr. Wang, which follows the idea that intelligence is the ability for a system to adapt to its environment while working with insufficient knowledge and resources. As such, it has to work with finite processing demands and storage capacity. It has to be open to new information, which can always challenge existing beliefs, and it has to work in real time without interruption. The system is designed to work under the assumption of insufficient knowledge and resources. The control strategy of this reasoner is attention-driven, meaning selective processing based, and the memory structure exploits compositionality, as we will see. The non-axiomatic logic is a logic which supports to reason about uncertainty. Statements in this logic can be inheritance, like cat is an animal, or implication statement, which can also express temporal relationships, like that lightning leads to thunder, and sets such as Sam and Garfield are cats, or that cats have multiple properties, like they are meowing and they are furry. Also, relationships can be expressed like that animals eat food, and temporal relationships like temporal sequences and implications, event A and B happening in a certain sequence, and that A leads to B. There are also other relationships, but those are the most important for this presentation. Most importantly though, the truth value in non-axiomatic logic is not binary. Instead, it's based on a positive and negative evidence amount. And based on those evidences, you can define a measure called frequency, which is the positive evidence over the total evidence, and a confidence measure, which is essentially the total evidence mapped to a value between 0 and 1. For instance, this allows the system to distinguish the case of 10 coin flips with 5 heads. With the other case, we had 100 coin flips and 50 heads. In both cases, the frequency is 0.5, but the amount of samples in the second case is much higher. An important aspect of all this is the ability to learn temporal relationships, or at least this is one aspect I have focused on for my NARS design or implementation design. And as an example, if you see an event sequence ABC, this event sequence provides positive evidence for the implication that A leads to B, and it also provides positive evidence that A and B together leads to C, and also positive evidence that A leads to C. But what if A happens but B does not happen? In this case, we see negative evidence to be generated for the hypothesis that A leads to B, because A was happening but B did not, differently than it was predicted. In this case, we can say that the frequency of the hypothesis is representing the success of the temporal implication to predict the outcome, while the confidence encodes the amount of samples seen so far. This capability to learn from temporal relationships was an important design criteria for this OpenNARS for applications design and implementation. And this OpenNARS for applications is a general purpose reasoning system which utilizes the non-axiomatic logic, and it's a pragmatic design which follows the NARS theory. It contains only the stable aspects of the theory and has a strong focus on agency, that is, systems that make their own decisions to reach certain outcomes. The implementation of this system is a high-performance multi-threaded implementation in C. The desired capabilities are, as I already mentioned, to learn from event streams in real time without interruption, and to be able to extract sensory motor contingencies out of those event streams. Some of those events correspond to own motor actions, and this is how essentially sensory motor contingencies are extracted. They essentially encode under which context or other happening events a certain operation event leads to other events to occur. And those sensory motor contingencies can be used to plan ahead to reach goals. Overall, this can enhance the autonomy of intelligent agents, including robotic solutions, as it allows those solutions to learn at runtime. Overall, the architecture of OpenNARS for applications looks like this. We will go through this. At first, let's look at the reasoning cycle. So at 1.1, you see sensory channels. In those, we form perceived events from multiple modalities. Then we go to 2 and combine those events into sequences to be put into an attention buffer, which is in the middle, number 3, also called the cycling events queue. From there, we take out events based on their priority, so that higher priority events are preferred, and we create a corresponding node, a concept node in concept memory, or if a concept with the same term already exists, we update the existing one. And for inference, we select a second premise that is either semantically or temporally related to the event we have taken out from the cycling events queue to perform inference. Dependent on whether it's a semantic or a temporal relationship, it will either go to semantic inference or sensory motor inference. The result of those inference results, go back to or enter essentially the cycling events queue, or also called the attention buffer. But we will go through this in more detail now. So the left is again the sensory channels, which is essentially that for each modality it realizes a mapping from physical signals to NARS events. This can be something simple like a touch sensor, which maps to a touched event, but it can also be a more complex mapping, like from camera to NARS via convolutional neural network based multi-object detector or even tracker. So we have those events from the different modalities, and they enter the Fifo sequencer. The Fifo sequencer receives those events from different sensory channels, vision, sound, and so on, and it stores up to a predefined maximum amount of newest events. And from those events, it generates sequences of the received events. This allows for a form of multi-model integration. And it does so in a very simple way. simple and effective. Like in this example, we have input events ABC, and the Fifo sequencer outputs A, B, C, which are the individual events, but also sequences thereof, like AB, BC, AC, ABC. So those sequences now enter the cycling events queue to compete for attention in the attention buffer. So this can be seen as the attention buffer can be seen as the only and central attentional control point of the system. It stores up to a predefined maximum amount of events, and it ranks events according to their priority value. In each cycle, it takes out the highest priority event and evicts lowest priority events when a new one of higher priority enters. So we took out an event from cycling events queue, and now we will see what to do with it in concept memory. So if we look at the memory structure, essentially statements form concepts, and except of implication statements, which are actually links between nodes. And those nodes allow for a local form of processing. They allow to summarize evidence via revision, and they also allow to do inference with neighbors, which are either connected through a common subterm, so are semantically related, or through an implication link, which means a temporal relationship. In this case, you see that if the door is closed and you call the open operation, the door will be open. So each of those events, door is closed and door is open, they are represented by two separate concepts with a shared term, which is door 1. But also they are linked through an implication link with an operation open attached to it. So if the door is closed and you open it, it will be open. This is how it's represented in memory. And this is generally the way its implications or procedure knowledge is expressed. That is, you have some precondition under which the execution of a certain operation leads to a certain consequence. The function of the concept memory, there are multiple functions it has to fulfill. First, to make sure that events are mapped to concept nodes of the same term, so that the evidence can be summarized with revision, and also, of course, to create a new node if a node with such a term does not yet exist, and to retrieve beliefs from concepts which are temporally related with the event we have taken out from the attention buffer, or which share a common subterm. And that, as I mentioned earlier, the temporal related beliefs are sent with the processed event to the sensory motor inference, and the semantically related to the semantic inference. So let's have a look now at semantic inference. This one always is based on a common term between the premises. So for instance, if we look at null 1, which is only about inheritance reasoning, so in the first line you see, if S is a M and M is a P, you can conclude that S is a P. But you see in this inference that both premises share M. Additionally, this is also true for the hypothetical inferences like induction and abduction, where in the second line you see that A is common, and in the last one C is the common term. So semantic inference is always by a common term between the premises. And now let's look at sensory motor inference. In this case, the relationship is temporal. between A and B. So for instance, if you have an event A and an event B, and B happens to happen after A, you can derive evidence that A leads to B. But if you already have such a relationship, and say A happens, and you already know A leads to B, then the system can predict B. This is both forms of sensory motor inference. A more complicated form of sensory motor inference is Gore derivation. If you have a Gore G, and you know that S leads to G, then you can derive S as a subgore. The second case is, if you have a Gore to execute a certain operation in a certain context, and the context is fulfilled, then you want the operation to be executed. So, and what's the general picture here? The idea is that if you have multiple candidates how you can achieve G, you have multiple implications how you can get G in different circumstances. The system makes a choice. It selects the operation which, given current circumstances, most likely leads to the happening of G. This usually means that the corresponding knowledge or corresponding implication or hypothesis has a high frequency and confidence, and also that the context in which we call C here has a high frequency and confidence. At least so high that that up can be seen as the candidate which most likely leads to G to happen. If, however, none of them is good enough, none of the candidates is promising enough to get G, meaning the truth value does not suffice, in this case the subgore or the context is derived as a subgore. So C is derived as a subgore, so that essentially the decision making can happen over multiple steps, because often you can't get G by a single step. Often you need multiple steps to get from current circumstances to the goal you want to achieve. And we will look through an example here. Say you have already learned or were given with knowledge, both is fine, that is, that in circumstance A, operation 1 will lead to B, in situation B, operation 2 will lead to G, and if event C happened and operation 3 is executed, you will get G. This is the corresponding graph to this, and what we can say is, so essentially now we have this graph, and we can ask ourselves how would the system make a decision if, say, G is the goal. Let's say A is already the case, or just happened, and the system wants to get G. So it will now evaluate the incoming links and see and try to use the operation op2 and op3, which best or most likely will lead to G to happen. However, in this case, neither B nor C was recently happening, so there's no good option currently to get G. So all the system can now do is to subgore. So it will derive B and C as a subgore to be processed. It's because G cannot be reached in a single step from current circumstances. So now, if C is processed, of course, as you see, it has no incoming link, so there is no way to make C happen. However, if we look at B, there's one candidate, and so this is also the best candidate, which is op1. The context is fulfilled, and so we can use op1 to reach B. So the system executes operation 1 with the expectation that B will happen as predicted. Now let's say it indeed happens as it predicted. In this case, the link that A will lead to B when operation 1 is executed will be strengthened. So this relationship is now strengthened and we are in a new situation. Now B happened, we still want G to happen. And now we see that suddenly operation 2 is the best candidate to get G, because B is more fulfilled than C, and also of course the link strength of the implication links also plays a role, but in this case operation 2 is the winner, and the system executes operation 2 with the expectation to reach G. What, however, if G does not happen, even though operation 2 was executed? In this case, the implication gets weakened, because operation 2 did not lead to G in the circumstance of B. So this link has received negative evidence, which gives us this picture. So in total, we wanted G, we started with A. System realized there is no direct way to get G, so it generated B and C as a subcore. Then it realized, okay, it can achieve B by executing operation 1, and it got B. Then it realized, okay, now I can get G by executing operation 2, and did this, and then realized, although it did it, it did not lead to G, so the implication link was weakened. Next thing, how to deal with variables. All NAS, or non-axiomatic reasoning systems, have a way to abstract its knowledge, and they can represent easily abstract relationships that, like, if something is black, then it's a raven. And such knowledge can easily be learned from examples. If there is some instance which is observed, as some raven is seen, and it's also seen that this has black. This instance has a black color. This is by itself sufficient to form this hypothesis. So next time, if it sees a black instance, it can already abduct via abductive inference that the instance 1 might be a raven. And also, if it would know it's a raven, it would expect it to be black. And the way this happens is so the forming of the hypothesis uses something we call introduction of a variable. So instance 1 is replaced with a variable to form this implication. But also if you use the knowledge, then the variable gets instantiated with the specific term. Like if it says that instance 1 is black, then this variable will be instantiated with instance 1 in order to derive that instance 1 is a raven. The usage of the system is quite straightforward. You can have events, beliefs, cores, beliefs which encode current state of affairs, cores which correspond to events the system wants to occur, and questions which are essentially statements the system should answer. And the output of the system are operations to make cores realized, and answers to the questions it got. And the event is always consisting of a term of a certain truth value, and the rest is not important for now. And operations are essentially a function or a procedure with arguments with which the reasoner wants to execute. And it has to finish in a small constant time, so don't disturb the real-time reasoning ability of the system. Do not block it, so to speak. And answers are always the best answer according to what the system currently knows. if we look at approaches with capability overlap now, then one important aspect or one important idea is already a quite old idea. It was proposed by Piaget, this idea of schemas, which is actually related to the implication statements we have just seen. And Thrasher formalized this idea for the first time in 1985, and which led to his so-called schema mechanism. And schemas essentially describe a transition from context to result via an action. So it's very similar to the procedural implication we have just seen. So there is some context. In this picture we see PQ is the context. And under the context PQ, the result X, Y, Z will result when the action W is executed. However, this relationship is not true or false. Instead, there are two probabilities associated to those schemas, which is, what is the probability to get X, Y, Z when PQ is the case, when W is executed, and when W is not executed. So this approach will then, what is a schema mechanism, will then, when it uses the schema, evaluate how much more likely is it to get X, Y, Z in circumstance PQ when W is executed over the case when it's not executed. And dependent on whether the difference is large enough, it will decide to take the action to get X, Y, Z. So this is essentially how it works. And those schemas can be changed by a planning process or chunking process, where the chaining happens from a currently satisfied context to a certain goal state to achieve. And the issue here is, of course, how to build those schemas. And Thrasher took a pragmatic approach, that is, if the predictive power of a schema is not large enough, meaning its probability is not high enough, it's often an indicator that there is some contextual cue missing that needs to be added in the precondition of the schema in order to enhance its predictive power. And this is called Schema Extension. So instead of NAS, which derives a new implication, the schema is extended and modified. So it's small difference, even though the representation is similar to those implications with operation involved, as we have seen. Interestingly, Thrasher noticed an issue with using probability. He noticed, while probability is a good candidate to draft the overall idea, he also noticed it's not really practical, it's not good to make it scale, because if you adjust the probability, you also have to adjust others so that probability axioms are not violated. For instance, that the sum of the probability sums up to 1. And so he noticed this is not really practical. So what he proposed is to switch from probability to a reliance measure, which is success over success plus failures. And this is essentially the same almost like frequency measure in NAS, which is positive evidence over positive plus negative evidence. And then he noticed that this alone is not sufficient. Because what if you had one example where something worked? The reliance will be 1. 1 success, 0 failures. Reliance will be 1. 1 over 1 is 1. And So even though just one example was seen, this schema will already be used and seen as highly capable, and this will often not work well, because often this was just luck. So what he proposed is to only use the schema when success plus failures is large enough, and this is essentially a hack, because it's better than not considering the sample size, but it's not as good as taking both reliance and sample space into account both. NAS actually solves this. It replaces this large enough decision via a truth expectation which takes both the frequency and the confidence of a hypothesis into account. So it solves this issue of what a good value for large enough should be. Interestingly, schemas have recently been used in a interesting machine learning paper in ICML 2017, which is Schema Networks zero-shot transfer with a generative causal model of intuitive physics. And what they use is a integer linear programming solver to find fitting schemas which are consistent with the observations in the entire history of the agent. Of course, this does not really work well in stochastic environments, because there might not be such schemas that will be consistent with all your observations, especially not in stochastic environments. So this is a limitation. Additionally, of course, with every observation, the optimization problem gets larger. So it cannot support cumulative learning, but the learning has to stop at some point where it becomes impractical to continue. So even though this one cannot continue to learn incrementally forever, it's never, and it can also not deal with stochastic environments. It's nevertheless interesting because it can deal with new cases often in a zero-shot way due to the compositional schema representation. In their paper, they show breakout with rock, and they compare it with a deep reinforcement learner with an actocritic approach. And interestingly, if they change the rock arrangement in the breakout example slightly to such a degree that it, in such a way that it never appeared in the training set of, or the training data of the deep reinforcement learner was trained on, then it will fail to deal with this case. It will demand additional training to handle this case, while the schema network actually is able to deal with this new rock arrangement without any additional training, since it has learned a representation which is able to take into account those properties of those rocks, essentially, to describe to have a partial description which it can use in order to make to allow for this kind of zero-shot transfer. So this is quite interesting. So schemas are very powerful in what you can do with them. And another technique, of course, we need to compare with is reinforcement learning. Reinforcement learning solves an important issue, which is the temporal credit assignment problem for behavior learning. Most of them, not all, there is also newer research, but most of it is for one outcome, the reward signal. And so it really tries to solve it, to learn state action mapping in such a way that for each state it will select, or it will have the action which maximizes the reward. An issue with, for instance, Q-learning is in practice you need to decay the learning rate alpha manually over time according to some fixed schema. And this is different to NAS, where confidence acts as a way to stabilize a certain hypothesis. Overall, we can say that Q-learning depends on some implicitly example-dependent learning rate decay and exploration rate decay to work well. So, to show, for instance, in NAS, a new evidence always weights equally much. And how much it is able to change an existing belief is dependent on the amount of evidence which already supports that belief. Meaning that a belief of high confidence, which already has a lot of evidence collected to it, will be more stable and more difficult to change than one which has not much evidence yet. Additionally, we can say that there is no explicit time dependence here. So we don't need to decay a learning rate here. It's the evidence amount which causes a hypothesis to become more stable. Also, owner can reduce the exploration. So OpenNAS for application can reduce the exploration rate by itself because it knows how confident the different hypotheses are. So if a hypothesis is already quite stable and predicts quite successfully, then it can then it does not need to explore that much in this case, and it does not need to have a time-dependent reduction of the exploration rate, because if the hypothesis is more stable, it can use it without having to explore. So it's the confidence which decays the exploration and not just the passing of time, which will make it unable for the Q-learner to adapt further in the future. So what we can also say is that learning rate decay and exploration rate decay is incompatible fundamentally with cumulative learning as NAS tries to achieve. I did some initial experiments in Bang. Interestingly, at first I thought it would not be comparable, but actually it turned out that owner tends to learn quicker because it's not that sensitive to those learning rate and learning rate decay choices, and reaches high success rates early on average. I have tried this with two variants of Bang. The first one, even though the reinforcement learner in the end got similar success ratios, it needed like 20 times as long. But important to say here is, usually if you apply reinforcement learning, you tune the hyperparameters for a specific example. But this I did not do here. I run a grid search of parameters which maximize the score over all procedural learning examples. So I tried to come up with a general score which measures the total capability of an agent without having any hyperparameters changed between examples, because this is kind of a cheat. You could change code, you could change parameters, but this I don't allow. I want one system which is able to adapt to different domains. And interestingly, the reinforcement learning approach was not really compatible with this idea, even though it didn't work very bad. But we see that that owner, how to say, at least the learning speed is quicker, even though the end performance is often comparable. In Bong 2, we have this example where we see that owner learned quicker, but the end performance was comparable. And in the first Bong example, it's just the owner learned like 20 times faster with this particular set of hyperparameters, which I optimized over via grid search. I also tried other examples like Cardboard, which was also part of this set of examples. Interestingly, in Cardboard, only in 2 runs the Q learner succeeded. In most runs, it really took like 50 times as long to get to similar success ratios. And in the Space Invaders case, or Alien as we call it, both systems ended up with a comparable end performance between 0.6 and 0.8 success ratio. But again, we see that owner learned faster, even though the hyperparameters were not adjusted at all. Another example, or another technique we necessarily have to compare with is belief, desire, intention models. It's one of the main AI paradigms for autonomous robots. It consists of beliefs, which encode current facts the agent knows and current perceptions, desires, which are potential goals to plan for, and intentions, which are essentially the desires pursued as goals by the selection of viable plans which get the goal achieved. And interestingly in NAS, there is no difference between beliefs and plans, because plans are essentially sets of procedure knowledge. They are just beliefs. They can be learned, their truth value can be updated by experience, while PDI models usually assume knowledge sufficiency, which is the designer has to put in all the information it needs to complete a task, and if the knowledge it has is not sufficient, it will fail, while NAS is able to learn new procedure knowledge from observations and trial and error and so on. So we can say that NAS is like a PDI model which learns. But so it has some desirable properties which also PDI models have, like the ability to pursue multiple objectives. So it's especially important for autonomous robotics. One reward is usually not that interesting. Usually you have multiple objectives which need to be achieved and they compete with each other, and you have them at the same time. And the behavior suitable for one goal is often not suitable for another. So reinforcement learning is already mostly disqualified, at least in the most typical form, because it's not only about learning a state action mapping anymore. The behavior is fundamentally dependent on the goal the agent tries to realize. Another observation is that in autonomous robotics especially, learning speed is a crucial metric due to physical body integrity and time constraints. So in those cases, large-scale trial and error is not an option at all. And this is also why you see reinforcement learning hasn't been very successful in robotics, and this is the reason. So, of course, if you have a perfect simulation or something, perfect simulation like in a board game or Atari game, you can train the AI, let it play against itself. Great. In the real world, this doesn't work this way. You don't have a perfect model of the simulation or the reality, but you still want your agent to be able to learn at runtime. So it's crucial for it to adapt quickly, we can really say in this case it's even the task achievement being primary and the optimality being secondary. Additionally, we can even say that the absence of reliable real-time learners is forcing roboticists to avoid learning at runtime and to stick to task-specific hard coding. And when a machine learning or deep learning model is involved, it is either trained offline or only used to adjust predefined conditional probabilities. So it's not really able to learn anything new at runtime. And this is something ONA as a NAS implementation addresses, besides the other points mentioned. At first, I have tried ONA on simple simulated cases to get an idea about its capability, because I wanted to make sure that it runs well for relatively simple examples before moving on to more complex ones. In this robot simulation, the goal is to collect green objects while not colliding with walls and rocks. So in this simulation, the system learns to avoid wars and learns how to find and collect green objects. Interestingly, it's able to do so within seconds or a minute, despite no reward hacks being applied. So it's really, really fast in learning this behavior of observing its environment in the search for green objects while avoiding obstacles. After I have been confident in the capabilities of the system, we have moved towards hardware integration. So we developed modules for the robot operating system, which is commonly used in robotics, and have added a module for the reasoner so that it can easily be applied in robotic applications, and also modules for sensory channels which are compatible with the reasoner module. This includes a vision module and also a landmark detection module so far, and more is to come. The vision module is based on convolutional neural network, which can reliably detect a fixed set of object types in camera input. And we have also played with ranging to enhance the detection, so that it also knows how far objects are away. Essentially, the way we did this, we encode the output of the convolutional neural network into NAS events, which NAS can consume, and we will see this. So we have moved this further with a simple Lego robot example. In this case, the hardware is essentially two motors for driving, so it can drive forward, to the left, to the right, and a gripper in order to catch and release objects. Also, there's this ultrasonic sensor that allows it to do ranging, so that it knows how far away objects are, the objects it sees, and also the obstacles. And the seeing itself is carried out by the smartphone, which is attached to the robot. So essentially the machine learning model or the convolutional neural network runs on the phone, so that it knows what it is actually seeing. And the ultrasonic sensor can tell it how far this object is away. The software here, we use this YOLO version 4, a tiny in this case, so that it's fast enough to run on the phone. And ONO is used for real-time reasoning, learning, and decision making. As a library to control the robot, we use the NXT Python library as a device driver. And now at the beginning we have simply tried to see how well can it learn to navigate. We gave it essentially two goals. It should not stay in one place, and it should avoid too low ultrasonic readings. From those two goals, the behavior it exhibits is emergent. That is, to move around while avoiding obstacles. At the beginning it struggles a bit to see how it can reduce the sensor readings, how it can increase the distance reading, so it wobbles around a bit until it figures out, okay, here it made one more mistake, but then it figures out, okay, it can move to a side, or it can turn around to increase the reading. And this way it can fulfill both the goal to not get too low readings, but also to not be stuck at one place. And let's see how this turns out. It might make one more mistake or so. Like here it turns to the right, but this is fine. As long as it doesn't move forward, and we see it correctly learned this association that, okay, if I see an obstacle in front, and if I move to the left side, or if I turn to the left, then I can increase the reading, and then I can, if I don't see something in front, I can simply move forward. This is what it learns. So those are very simple cases of sensory motor contingencies, which are in NARS represented by those implication statements we have seen. And so it manages to move around without making any mistake, without colliding into things. So this was just the first part of the experiment. Was crucial to make sure that it can safely traverse its environment without getting stuck and without damaging itself. Let's just let it finish. In this version there was still the cable attached to the robot, because it took me some time to make sure that the Bluetooth connection works. We will see this later. So in this case it's connected to the PC. And also for this robot there is no camera attached, so it was just first experiment. But now we will see a more interesting mission. The mission in this case, by using the knowledge it has learned to navigate without collision, we use this and we try something more interesting on top. The mission here is to find a lonely bottle, to pick it, and to find another group of bottles to return it to. In this case, the only background knowledge it has is the mission knowledge to pick actually a bottle, not an object, to pick a bottle if it sees it, and to drop it if it sees a collection of of multiple bottles. The rest is learned, how to navigate without getting stuck, to explore, and also how to focus on a bottle, so that if it finds one, that it can actually pick or actually focus on it before the background knowledge takes over and says, okay, now I have a bottle in front, I should pick it. Let's see how this looks like. So it avoids the collision, moves to the left. Now it has seen the bottle and has focused on it. Now it has grabbed it. In this version the gripper was not perfect yet mechanically, but it's able to, it has essentially catched it and is dragging it around a bit like a hockey player. Now it again sees an obstacle, so it tries to avoid it and to move to the left. So essentially it now tries to find the collection of bottles to return the bottle to. So it's pretty much a combination of learned behaviors and some very simple mission knowledge to drop the bottle to the collection of bottles. So this is a case where essentially the system was not equipped at the beginning to complete the mission. A large part of the knowledge necessary to complete it was learned at runtime. But I will elaborate on this. But first we will see a small update on this, which is a grab and lift mechanism, so that it can actually lift up objects and do so with a single motor, and also to operate without a cable with Bluetooth. Just a short video which shows those new capabilities. So it has seen the bottle, it has picked it up. Now I simply put a group of bottles down, it sees it, and this is where it returns the other bottle to. So this is a mechanical improvement, and also, of course, the improvement of the Bluetooth connection so that it can work fully autonomously. The interesting thing is that the learned hypothesis, that there are many learned hypotheses, actually much more learned knowledge than given knowledge. For instance, to move forward if nothing is seen, simply because this innate boredom gore forces it to do this, or to learn this, and then to exploit it. So it simply learns to move forward when there is no obstacle currently visible. Also it learns, okay, if I move to the left and the obstacle is front, then I don't see this obstacle anymore. So it automatically, simply by not wanting those obstacles to be seen close, simply by this it learns or it learns and uses this knowledge. Okay, if I move to the left, if I turn left, if there's an obstacle in front, I can avoid the obstacle. This is not something we give it, it's just something it picks up based on this innate drive not to have an obstacle close to it in front. And this innate drive to keep moving makes it move when there is no obstacle. So that's quite interesting, but it learns even more interesting and abstract relationships. Like, if it sees something on the left and it turns left, it will see it in the center. And this is even abstracted across multiple types of objects. So it learns this general knowledge, even though it has never seen a bottle, but it has seen other objects, for instance on the left. And then it has turned left, and it has seen same object then in the middle because it has turned to the left. Same if it sees something on the right and it turns to the right, then it sees this thing in the center. And this knowledge, it automatically then applies to the bottle when it needs it, even though it has never seen a bottle before. So in order to make the mission complete, or in order to make it carry out the mission, we don't need to tell it much, because most of the knowledge it has, or most of the knowledge it needs to complete the mission, it can learn on the fly. So all we need to tell it is really only mission-specific stuff. Like, yes, we want the robot to pick the bottle if it sees it in front, and we want it to drop it if it sees other bottles, so that it can collect them into, so it can return the isolated bottle to the group. And all the information, all the other information, how to focus on an object, how to explore while avoiding obstacles, is all learned. This means that you can describe a mission to the system, and you can send it on this mission, even though you have not provided it with all the information needed to complete it. It will explore and it will try its best to complete it itself. It will pick up relevant knowledge by observation, by its own sensory motor interaction, its own trials, and its own observations of other agents. Another experiment we tried is we've recently added a small natural language interface, which is based on a shallow semantic parsing approach. And in this experiment, I want to ask arbitrary questions to the system about its environment, and it needs to reach out and try to find an answer to the question. So this sometimes means it has to move, because it might be a question about something which is not currently in set. We see a simple example here. I ask it if there's a bore near to the bottle. And currently it doesn't see the bore because it's currently centered at the bottle. But you will see it move in order to try to answer the question. Is there a bore near the bottle?
Yes.
And this type of active question answering is very central. It's easy to build a system which just answers a question about a currently observed scene. It's more difficult to make it actually reach out for the information in order to be able to answer the question. This kind of active question answering is something I want to explore more in the future, and NAS has the necessary theoretical basis to make this a reality. Recently I have had very good success with an artificial, let's say, a constructed, or yes, artificial curiosity, so to speak. Previously we already had motor bubbling in the system, which is that it sometimes tries a random action, which is a form of exploration. But this is not very smart to do. Even though it's very widespread in reinforcement learning, it's not a smart thing to simply try random action uniformly. At the beginning it's necessary because there is zero knowledge available. But in NAS, because it actually knows the confidence of the different hypotheses, we can make it actually try operations corresponding to the lowest confident hypothesis, which contextually apply. So we force it to test uncertain hypotheses from them to them. And that's interesting because essentially else it will find some behavior which kind of works and it will mostly stick to it. But if it's sometimes trying out uncertain hypotheses, we actually force it to learn more about its environment, and this has turned out to be very fruitful. While an agent without this curiosity will often get stuck and essentially repeat the behavior which has been successful so far, the curious behavior or the curious agent will try more, will try things it hasn't yet tried, and will hence learn more about its environment and learn things the other agent will not learn. And even in the simple robot simulation I have seen you can see a clear improvement with the curiosity approach, which shows it will explore the area more effectively, it will try things it hasn't yet tried, and will be more effective in finding and eating food. So very simple example so far, but it already shows that curiosity is an important addition, and we think that we understand curiosity now, which is a good thing for AGI progress. With all this in mind, I can say that overall my research focus has changed from making non-axiomatic reasoning practical to maximize autonomy beyond the state of the art. I want to perform research related to autonomy in the future, which also includes aspects which I only briefly explored so far. Clearly, what we have seen in the last slide, I want the agent to explore its environment, to do exploration and play systematically, so that it can learn more about its environment by exploiting hypotheses where it's more uncertain about, essentially testing the more uncertain hypothesis, and not just random action invocation, which has nothing to do with actual curiosity. Additionally, it should be able to physically manipulate and utilize objects, which is a form of tool usage, which I have shown so far with this bottle collect mission, but this is just the first step. I want to do more in this direction. In all those, when autonomy is concerned, you can only have true autonomy if the system is able to learn or adapt at runtime from observations and interactions. Ideally, this is not only from own observation and interaction, but also by watching other agents, could be other robots or humans, to perform a task and extracting procedure knowledge from this and other information. So it's also learning from observation, which I'm after. Additionally, the system should be able to effectively model the world, which means to remember places effectively, objects, other agents, and their properties, so that it can effectively perform tasks in complex environments. And I will make sure that the system can do those things very well. Clearly, a core of autonomy is the ability to also operate without a human, meaning a form of independence. If there's no human present, the system still needs to be able to fulfill its mission and learn, or at least try its best to achieve it, even in cases where its knowledge is insufficient to get the task done right away. So it has to seek out for more information and knowledge, and it has to do so, or it has to be able to do so even without a human. Nevertheless, of course, it would be good if it could extract useful information out of human speech to work together more effectively with humans, to answer questions, and to use language in other ways, which I also have started to explore. And this concludes the research, or my new research focus, which is to progress everything which could enhance the autonomy of intelligent agents. I thank you for watching my presentation.